Okay, if I can have your attention please, we shall get started. Our speaker today is Eric Ayars, who comes to us from 15 years at Chico State. Sounds like a bad melodrama, but nonetheless, we're very glad to have you here today. His academic background originates with a PhD from North Carolina State University, followed by 3 years as an instructor in Walla Walla, Washington, before joining the faculty at Chico State. It's wonderful we can have faculty from other CSUs come to present, and in return we will be having faculty present in their programs as well, which I think is an excellent chance for our students to meet other faculty members who have a similar background to many of the faculty that they work with. So with that said, let's give a warm welcome to Eric.
I have to say, my academic career actually started a little bit earlier than that. I'm a graduate of Pacific Union College from just across the Napa Valley, and Bill Mundy is here. He was my mentor, and he's the one to blame for me becoming a teacher in the first place. So anyway, it wasn't just me that did this. I got to spread the blame around a little bit. Tori Goff and Kirk Williams were two of my students. They are both planning to become high school teachers, and they came to me looking for an interesting project about the time that this one fell on me. So this is partly their fault too. I'd like to start talking about some useful bits of quadcopters and things you can do with them. If you've been living under a rock for the last couple of years, then you wouldn't know about quadcopters. But if you've watched Olympic coverage at all, okay, you'll occasionally hear this brrrr sound in the background while they're showing slopestyle skiing or whatever else. That's because they're filming it from a quadcopter. Very maneuverable. They can carry a surprising amount of weight. Here's a picture of one carrying a full digital SLR camera. In addition to aerial photography and videography, one of the things we've done at Chico State with them recently is crop health measurements. We do a lot of orchard farming in Chico area, walnuts and almonds mostly, and pesticides being expensive, we want to know where do they need to be most applied, where are things doing well. And it turns out in infrared, crops look different than normal. I mean, they're just all green to humans, but if you look at them in infrared, you can actually tell, well, these trees over here are suffering from such and such. So you can program a quadcopter with GPS to actually fly a grid over an orchard and take pictures at intervals and tell you what's going on. Structural inspection is another use for them. Bridges, roofs, you can go up close and take pictures of cracks and leaks and everything else that would be hard to get a person into. And one that I was involved with recently with the geology department at Chico State was taking pictures of these bluffs. We have a lot of cliffs and bluffs above Chico. It's old lava flows, and the geology department is just fascinated by those because they're rocks. And I was fascinated because they would pay me to fly a quadcopter, which I would do for free. So it turns out that if you take several thousand pictures of high-resolution pictures of a cliff from different angles as you're flying past it at different levels, they have this software. You can just throw all the pictures at the program, and it sits there chewing on them for a while, and then it builds this complete 3D picture of the cliff and can analyze from that. Well, look, this is one lava flow and this is another lava flow, even though they look the same now. So they were interested by that. There's a lot of stuff you could do with them. You can also just have a lot of fun flying around, which is how I got involved. Control for quadcopters. As you know, there's 4 propellers, and simplest situation is they just all have the same amount of thrust and the thing sits there. Okay? So for vertical control, you just adjust the amount of thrust. You lower the amount of thrust, and the quadcopter goes down. Raise the amount of thrust, and it goes up, and so on. That's a really gross oversimplification of what's going on with them, because they're not stable. There's no inherent stability to a quadcopter. Like with an airplane, you've got dihedral, you let it go, it'll just go. It's designed right. A quadcopter, you let it go, it flips over immediately and crashes and burns. Okay. For pitch and roll control, you would start out with, here in level flight. Pitch and roll are really the same thing for a quadcopter because it's symmetric, but you basically raise the thrust on one side, lower the thrust on the other side, and as a result, it tilts. Okay? So, one thing I want to say about this, while I'm queuing up video here. From a physics standpoint, these are really particularly interesting because, here we go. There's only 2 forces acting on the quadcopter. There's gravity, which pulls straight down, and it's pulling on all parts of the quadcopter equally, and anything on top of the quadcopter. And there's the thrust, which is perpendicular to the plane of the quadcopter. And so anything that this does has got to be the vector sum of those two forces. And this is a bit of a clip that I stole. Where's the play button? Okay, and we couldn't get the sound working right on it, but it's okay, they're all taking control. These things are much more complicated than just, well, let's adjust the four props, okay? Because they're completely unstable. Any change in one of the props is going to cause it to flip over uncontrollably unless you're constantly monitoring the speed of all four propellers and adjusting it so that it stays balanced. It is not inherently stable. It has to have a dynamic adjustment on the fly all the time, about 100 times a second. I've actually built a controller for one of these, took everything I had to get the thing to sometimes hover occasionally, and then I threw my controller out and bought another one and had much more fun. So anyone interested in engineering or electrical design or anything like that, it's a PID controller. So it actually measures the current angular position and rotational rate on 3 axes for the quadcopter and adjusts constantly on the fly for that. So
what's PID?
Oh, PID stands for proportional integral differential. So the proportional term is, okay, there's the error term, which is how far away you are from where you want to be. So you program and say, I want you to be level. And it could measure how far off level are you. And then the correction for that is proportional to how far off level you are. The integral term is how long have you been off? And do I need to give it a little bit more because even though I'm saying go that way, it's not getting there. And then the differential term is essentially how fast are you going and should I slow down a little bit so you don't overshoot? So the combination of those three allows you to control it very smoothly. And it has to be done by some kind of computer or microcontroller because otherwise it just, well, it happens way too fast for humans to do it. Okay? Now, the yaw control is where things get a little bit more physicsy. Okay? I have to explain this. Okay, everyone get their right hands up. The physics professors, you don't have to, you know this already, okay? Well, what you want to do is put your hands so that your fingers are curling in the direction of the propeller spin, and your thumb points in the direction of the angular momentum. Okay, for those of you in physics majors, like, yeah, get on with it. But, okay, so the way the quadcopters work, you have 2 of them that are actually spinning up, okay, and 2 of them that are spinning down. Now, in this diagram here, the up and down arrows don't mean the thrust. 2 of them, they aren't pushing down. It's just we say, for the yellow ones, that's the down momentum, or down angular momentum. Okay, just to keep track of which way they're spinning. And use your right hand to figure it out. If you use your left hand, people will know you're really a chemist. Okay, so anyways, or some kind of engineer sneaking into this talk. So here, the size of the oval represents how much thrust there is. So a big oval would be a lot of thrust, a lot of spin. A smaller one would be slowing down. So just trying to give a picture of how that works. Okay, so, oh wait, back one. In this particular situation, the total angular momentum for the quadcopter is essentially 0. Okay, because you've got 2 that are down, and then the 2 that are up that have about the same amount of angular momentum. And so they all add up to 0. And then the body of the quadcopter isn't spinning at all. So that has 0. Okay? Now, this is was one of my favorite demonstrations for teaching introductory physics. I'd actually bring a quadcopter in and sit here flying in front of a whole pack of students and say, look, here's an example of conservation of angular momentum. Angular momentum, if there's no external torque, is conserved. So if we increase the angular momentum of one set of props and decrease the other, okay, well now we've got a lot more down spin, okay, and a lot less up spin, but the angular momentum needs to be conserved, so something else has to be spinning to make up for the missing up spin so that we still have 0 angular momentum. It's this wonderful demonstration of conservation of angular momentum. You can sit there spinning a quadcopter in front of students and they all say, ooh, okay? So there's the result. So there's how you turn a quadcopter. Well, Conservation of angular momentum holds if there's no external torque. And if you turn the power supply on the props off, they stop, which means there's an external torque, or there's a torque of something. Something's got to stop those things. So you get to thinking about this, I got to thinking about this and thought, wait a minute, does conservation of angular momentum really apply in this case? Let's look at this yaw control again. The props are spinning against air resistance. So there's a torque due to the drag on the props. And that air resistance is, depending on Reynolds number and a bunch of other complicated stuff, probably goes as V squared for the prop velocity. So in this case, those rapidly spinning yellow props are going to be creating a torque, or the air around them is going to be creating a torque in the upward direction. Whereas the blue ones are going to be, there's going to be a torque in the downward direction, or not direction, but down torque, or down angular momentum. And so the net result is we've got a lot more torque this direction due to the yellow ones than we do that direction due to the blue ones, and so the whole body of the quadcopter is going to be turned that way, just like the conservation of angular momentum explanation for how it goes. So now we've got two different explanations for how this thing turns. They both cause yaw, they both cause turning in the same direction, and which one's the primary effect? Now this is where we actually started on this research. It's like, okay, can we figure this out? How would we determine what is the primary effect here? So here's our plan. Put a quadcopter in a vacuum chamber. Measure how well it turns. Measure the torque. Take the air out, measure the torque again. Okay? And then win an Ig Nobel Prize, because this is the kind of thing that nobody should ever do. All right? So we expected some complications. Quadcopters just don't fly in that. You cannot overstate how poorly they fly in that. Okay? LiPo batteries that run the quadcopters, they're even worse in vacuum. They're partly liquid. Okay? You put them in vacuum, they boil, they explode, they spread reactive metals all over the inside of your vacuum chamber and piss off the owner of the vacuum chamber, and it's just not a good thing. Okay? Then how do we actually measure the propeller speed and changes in propeller speed and the rotation of the quadcopter itself? Not to mention, how do you get the quadcopter in the vacuum chamber in the first place? So we chose this quadcopter because, well, really careful design considerations for this. One, it was small enough to fit in the vacuum chamber, and two, it was cheap enough we didn't care if it exploded. Okay? That was our design criteria right there. I can't remember what kind that is. It was $99 at A-Main Hobby, though, if you want to buy your own. Okay? Well, we came into it with knowing what some columns were going to be, so we decided we better have some solutions lined up. We decided we would mount the quadcopter on this Pasco, on this Pasco rotary motion sensor, just straight out of an introductory lab. Just make some little platform, tape the quadcopter on there. Anyone here do vacuum work? I mean, serious vacuum work? Okay, so you know tape in a vacuum chamber. You see where I'm going with this, right? Okay. 3D printed objects in the vacuum chamber? Yeah, we're getting bad. Okay. We 3D printed a little saddle that sat over the top of this. We taped it on too. And mounted photo gates, so the props were spinning through the photo gates, and then we could tell every time the prop interrupted the photo gate, we'd say, okay, that's how fast it's spinning, and figure that out. Rather than have the battery in the chamber, we would just run power from outside through an electrical feed-through. And now, of course, we have to run power to the quadcopter. So we use really fine wires, because you want to use fine wires so it doesn't interrupt the motion of the quadcopter. Right? Well, solutions cause more problems. For every solution, there is an equal and opposite problem. I think there's Newton's fourth law or something like that. Okay? This first one turned out to be almost a deal breaker. Okay? We had no idea how much power this quadcopter took. Okay? It turns out, it's a 3.7 volt battery. It takes 3 amps out of this thing. Okay? So it's running more than 10 watts. Okay? In a little quadcopter, it's about the size of my hand. Okay? Now, if you're running 3 amps through really fine wires, well, there's some resistance to the wires. You get a voltage drop through the wires. And in fact, the actual voltage drop is 2 ohms for the supply wires. So you think about that. 3 amps through 2 ohms, that's going to give you a 6-volt voltage drop. We only had 3.7 volts to start with. Okay. So we would turn the thing on, and at idle it runs 100 milliamps, and it's fine like that. You have to put the voltage up to about 4 volts instead of 3.7. Quadcopter's happy. You use a controller, you turn the motors on, it shuts down immediately because the quadcopter thinks, oh, the battery's dead. The voltage just dropped. The battery must be dead. Shut everything down. So we spent a week trying to figure out, well, why does this thing just turn off every time you turn it on? So that gets to be a problem. We couldn't adjust the voltage on the fly. You can't just say, all right, well, let's just run 12 volts on this, and while it's running, we get 9-volt drops, so it's 3 volts. Because then when you turn it off, it goes back to 100 milliamps, and the 12 volts now hits the quadcopter, which turns into this molten pile of slag. So we had to build this circuit to automatically adjust it. We used this is actually half of a Class B amplifier, for those of you who care about that kind of thing. But this is an operational amplifier. It just takes 2 voltage inputs. It doesn't take any current in, it just samples the voltage, and it adjusts the output here so that the 2 voltages are the same. So we take that output and put it into a power MOSFET here, basically just a switch that's controllable by that gate signal, so that this voltage, and that was actually 12 volts there, that gets supplied to the quadcopter here through the switch. And then there's an extra sense wire here that goes back to the op amp, and the op amp would just adjust the power regulation on that MOSFET until the voltage there was the same as the voltage back at the quadcopter battery, which we had just sitting there using as a voltage reference. It's like, well, this is the voltage you want. Here it is. Okay. So that set us back a couple of weeks. We had to figure out how to build this and make it work and so on. And for those of you who've done electronics work, you'll probably know. Oops, wrong button again. There we go. You'll probably notice we have another problem here. This voltage from the quadcopter, the current from the quadcopter goes back through this ground wire, which also has a voltage drop. So this isn't a perfect solution for this. And in fact, every time I look at this, I'm amazed that it worked at all. But it worked well enough that we could run it for short periods of time. Which brings me to another issue, which I'll get to. Here's our actual setup. Just a picture of that. Inside the vacuum chamber, we have a quadcopter on the rotary motion sensor. These wires had, well, they were power supply and sense to sort of adjust the power supply, and power supply for our photo gates to figure out how well is it looking, or how fast is everything spinning, signals from the photo gates. So all of that had to go through this electrical feed through. We ended up with 3 power supplies now instead of just 1. A supply for the sensors, a supply that actually ran it, the quadcopter, a voltage regulation circuit that took this supply and sent out the voltage that this needed for whatever it was doing at the time, the reference voltage there, which was just using the battery. And then we took all the signals and sent them to an oscilloscope to try seeing what's actually going on. We used a digital storage scope just to catch those signals. Okay, so that was successful, but there's always more problems. Okay? Quadcopters cool by convection. Okay? They have 4 fans on them, blowing, and that keeps everything cool. You put them in a vacuum chamber, those 4 fans are still blowing, but they're not blowing anything anymore, and they don't get anything cool. So the 3 ways you can cool things are radiation, which goes as T to the 4th power, and in order for the radiation to count, this thing's got to be glowing. We didn't want it to be glowing. Okay. The other one's conduction. Well, the only thing attached to this it was mounted on a little 3D printed plastic thing. We didn't want to conduct any heat through that equipment anyway. So that didn't work. And then the wires. But they were real long, thin wires, so we're not getting any heat losses through those. Basically, that 10 watts of power going into the quadcopter stayed in the quadcopter. All right? We did a rough calculation of how much of a problem that would be, and we figured it would take 5 or 10 seconds of full throttle operation to reach the temperature of solder, or melting point for solder. At which point, electronics really just stopped working, because everything falls apart. We also had the problem because now with all the sense wires and power wires and photogate wires, we have 8 different wires going to this thing, and it can't rotate freely anymore because there's all the wires going to it. And then, of course, if you're doing vacuum work, you're just laughing at the mere idea of doing this because we've got bearings that are oiled inside the vacuum chamber. We've got the 4 motors with their bearings. We've got 3D printed parts. And let me tell you, if there's anything worse than 3D printed parts in a vacuum chamber, it probably grew. I mean, it's got to be biology to be worse than 3D printed parts in a vacuum. Okay. So nothing was going to really work well. And so in time-honored undergraduate tradition, we just decided to ignore the problems and just see what we could do with it. Okay, we would run the quadcopter in really short bursts. So 2 seconds, tops. Try to get all the data we needed in 2 seconds, and then we just sit there for a while and let everything cool off. We had no idea what temperature it was. We just sit there twiddling our thumbs. We got bored and said, well, you think it's safe? Let's try it again. And we took the wires, you know, if you can't fix it, feature it. We couldn't fix the wires, so we featured them. We put the wires in this nice big kind of a watch spring spiral. Okay, so as the quadcopter is turning, it would wind the spiral up slightly, and it'd be like a very loose spring, very low tension torsion spring. And then the other way, you know, so we could since it's on a spring now, we could just look at how far it turned, and from how far it turned, we had an idea of what torque does it have, or at least relative to for different tests. And we decided to just run it rough vacuum because that's as good as we're going to get to get all these awful parts in there. This is a poorer picture on this screen than I would like, but the whole thing was built on a plate. The plate's about 12 inches in diameter there, and it fits on the bottom of this vacuum port right here. The main diffusion pump for the vacuum chamber is here. We got a vacuum chamber in my advanced lab that is basically Legos, and we put it together all these different ways. This is one of the ways it allowed us to do it. We could just replace this onto that port at the bottom and run it. So there it is, ready to go. And we finally got data. Isn't that gorgeous? The sad thing is that's good data. Okay? Keep in mind, what we're looking at is photo gates as a propeller, a little tiny, about a 1/4 inch wide propeller goes through the photo gate. So there's a brief pulse from a phototransistor on that. Those are the top two. We could only put it on 2 of the props because we had only 8 wires that went to our vacuum feed through for the electrical, so we had to decide what to do. So we chose 1 clockwise and 1 counterclockwise prop and hoped that those were representative of what was going on. So there's pulses from those, and you can see that fuzz there. Those are the pulses. Okay, and then the rotary motion sensor from Pasco, they've got some extra logic circuitries there. So instead of a regular quadrature signal, it just puts out pulses for how far it goes one way, and then pulses on the other line for how far it goes the other way. So we can count pulses one way, and then count pulses on the other line and see how far it came back and figure that out. So our scope, it's a nice digital storage scope on this. We saved it. It was about 10 megabytes of data per run, just number after number after number, taken every 100 nanoseconds or something like that, something ridiculous. I forget what it was. Thousands and thousands and thousands of lines of numbers. So we wrote a Python program that would just go through and figure out where all the peaks were, and then look at the timing between the peaks. And so from the time between the peaks, we'd figure out, well, that's how fast the problem is turning, or how fast anything else is turning. So there we go. Finally, there's real data. Okay? Now this is with air in the chamber. We put the whole thing in the chamber, left the air in the chamber, figured minimize changes as much as possible. We'll just start with the chamber. So the green line here is the speed. Green line is a clockwise prop, and the purple line is counterclockwise. And what we would do is we would start the scope, put the throttle up to full throttle, put the rudder to full right rudder, and then, meanwhile, Tori or Kirk is counting 1, 2, and at 2, we just cut the power again. Because we didn't want to run for more than 2 seconds. We were worried about that 5-second limit and having the whole thing catch fire. Though it won't catch fire, it turns out, inside the vacuum chamber because there's no oxygen. Yeah. Anyway, you can see here, when it decides to turn, when it's told to turn, right about here, the 2 props change their speeds. So one slows down, the other one speeds up, and the whole thing starts rotating. And keep in mind, it's got that PID loop, that control loop, that tries to set everything to behave in a way. When you say full right, it doesn't go as fast as it can to the right. It tries to go to the right at this angular velocity, right there. And you can see it tried staying there, but now as it turns, it's winding up that spring. Okay? And so it has to turn or speed up one prop even more and slow down the other prop even more to try to keep going at that rate as it's working against that spring. And eventually, right about here, it just gave up and quit. Okay, but that's, you know, a fair amount of turning there. It's almost 12 radians. Okay, so you know, 1 3/4 turns total. Okay. Now that was with air in the chamber. So remember these numbers here. That's 11 and a half roughly, and the prop speeds between 1,000 and 1,500. That's radians per second. Okay. So suck all the air out of the chamber, and ooh, that's ugly. Okay. To this day, we aren't sure why we get such garbage data on that. We think it's because the props are spinning about twice as fast. Look at that number there, 3,000 instead of 1,500. And so it may be that the scope's just missing some of the pulses. And if it misses a pulse, then it thinks that everything's going half as fast. Oh, look, there it is, half as fast. So we're pretty sure that this is speed related. It's going twice as fast because there's nothing that controls the actual speed of the prop. It just applies more power or less power. And at full throttle with no air in the chamber, they can spin a lot faster because there's no air drag. Okay, so they're spinning twice as fast. Now that's interesting too, because if it's spinning twice as fast, the angular momentum changes will have twice as much effect. So this angular momentum should have a significant effect here. Okay, now notice the magnitude though. It did less than 1 complete revolution on this. Okay, and not only did it do less than 1 complete revolution, it bounced back. So it's like it went against the spring and then went completely back to where it started again. Okay? Other things to note, here's where it started speeding the one prop up and it levels off pretty much. That's full throttle. The motor can't spin any faster. So the brain for this quadcopter is saying, turn, dang it, turn, go as fast as you can on one. The other one, notice that curve right there? That's an exponential decay curve, which is what you get for an oil bearing and something just spinning down with minimal drag. Okay? So we believe the power is completely off on this prop and full throttle on there. Okay? And this graph is consistent with an impulse on angular momentum right here, where it changes the rotational or the angular velocities of the two props. And then this is consistent with simple harmonic motion, going against the spring and coming back. Okay? And here's a comparison of the two graphs on the same scale. Blue one is with atmospheric pressure, and the purple one is rough vacuum. So, my nice demonstration of quadcopters turning as an example of conservation of angular momentum. Turns out on this graph, well, that's about 1/5 of that. But keep in mind that propellers were spinning twice as fast. So twice as much effect is 1/5. We can estimate then that we actually have, for quadcopter yaw control, 90% of it is just air drag, and 10% is conservation of angular momentum. So I can't use that for the demo anymore. I've got to use something else. Go back to standing on the turntable and risking puking on the front row. Okay, we had 6 successful runs. This was the prettiest one. Of course, you only show the prettiest one in the graphs. The rest of them were pretty ugly and hard. Yes, that was the pretty one.
No, the pretty one is the typical one.
No, I'm not gonna totally sacrifice my soul on that one. The pretty one is the one I want to show you. The rest were uglier, but they're all consistent with that. It's about 90% drag and 10%. Now, as far as repeatability goes, that 5 to 10 second thermal calculation was a little bit optimistic. Okay? It was still working when we took it out of the vacuum chamber, and so, of course, what do? You got a quadcopter, you fly it around the road. It had been damaged at some point. Some solder flowed somewhere. Something came loose inside. We're not sure what. First time we flew it for a few seconds before we noticed smoke coming out of the thing while it's flying around, and we crash landed immediately and haven't flown since. Yeah. A little bit of a problem. They're really not designed for vacuum use. So, that was what we did with it. What questions do you have? Other than why?
What if you were to do 2 atmospheres and 1 instead of 0 and 1?
Wow. Well, we wouldn't have as much cooling problem. That's for sure. We also couldn't do it in this vacuum chamber because, yeah, they're designed
Pressure
to.
chamber.
Yeah, we have to do a pressure chamber. I hadn't considered doing that, and it's an interesting question.
It'll be next year's project.
No, I think I'm done with quadcopters. But yeah, I encourage you to investigate that further and let me know how it works out.
I'm one of the students.
Yeah. Yeah.
Can you tell us more about the behavior of some of these materials in a vacuum chamber that you either did or didn't expect?
Yeah. You're talking about the outgas?
3D printed elements.
Yeah.
Printing is trapped.
Okay. If you have a really polished, smooth surface, you know it looks like this, right? Okay? Yeah, no. Okay, it looks like this on a very fine scale. Okay? So if you take a metal and you put it in a vacuum chamber, there's a bunch of air stuck in here, and there's water vapor stuck to the metal and everything else. And all of this stuff acts like a leak because it continually outgasses. It comes off the material into the chamber and raises the temperature of the chamber. If you're trying to get the chamber down to low pressures, well, you can spend days waiting for all of this stuff to essentially boil off the surface. Okay? Now, 3D printed stuff is designed to be bad for this, okay? Because what you got are all these layers of stuff that are kind of, like this, all stuck together with little tiny bubbles in between them, okay? And then they're plastic, which is bad in the first place because, well, okay, if you can smell it, that means it's outgassing, okay? We don't put brass in vacuum chambers by choice because you can smell brass. That's zinc vapor on it, I think. Am I right on that?
I was just thinking that I didn't know what it was, but I was thinking about how we don't put brass in it, and it does smell. I never thought of it.
I think that's it. It's the low vapor pressure of the zinc in it. But yeah, outgassing from plastics is bad. Thermal plastics are particularly bad. Some kind of plastic like Teflon isn't really that bad. Kapton tape is okay. So we use Kapton tape for everything. That was our sop to, yeah, let's do this right. But 3D printed stuff, it's just bad. I mean, you might as well put a frog in there as well. I spoke with Eric Black a few years ago down at Caltech. He was the one who did the mirror testing for LEGO. He built this chamber that you could walk into. It was that big. And then people were saying, well, yeah, let's put the optics table in. Yeah, great. So that's what I made it for. So we built this optics table in. Well, let's put this plastic mount in it. Like, okay. Oh, and here's an electronic piece. It's phenolic. We'll put that in. You can smell phenolic. Yeah, they kept adding more stuff. And you did get it down to 10⁻⁵, though, which was good enough for what he needed.
LEGO runs at 10⁻⁹.
Right, so you didn't have that stuff in it. Now, this is for testing coatings on the mirror, not for actually using it. And I think about 10⁻⁹ and just go home and curl up in a ball in the corner and cry for a while.
So what have you actually then flown these to do some scientific experiments besides trying to look at the angular momentum?
Yeah. One thing that we're working on right now with geology. Geology had the money for a quadcopter, so I'm doing stuff with them because, money. So, and they have a quadcopter, and it's their quadcopter, and I didn't have to buy it, so I get to fly other people's toys. That's fun.
That's a big deal.
So one of our researchers in the geology department is, he does LiDAR work, and he can measure the temperature of the air as a function of distance from his LiDAR unit. But he can only measure starting at about 100 feet out. So if he's looking at the temperature gradient of the atmosphere, he doesn't have the first 100 feet. And we've got models for how that works. And you can build a tower and put thermometers every meter on the tower, but then you have to move it around if you want. And so one thing we're playing around with is putting out big outriggers on this quadcopter. The outriggers so that we're out of the prop wash, and then just have temperature sensors out, 3 meters out either side. You can do that with a quadcopter. Set the PID control. It just thinks, oh, it's more stable than usual today. Good, but then we just fly that up. We can measure the altitude as we go with a barometric pressure sensor, measure the temperature as we go, and get a profile for the canopy layer above orchards, just right there, that first 100 feet. So that's one thing. Another thing was looking at the rock formations and being able to see other fault lines that you wouldn't see normally just because all the rocks look the same. They don't look the same to me anyway. Geologists can tell the difference.
And did you try any hexcopters? Because they're more stable than the quads, for sure.
We haven't tried a hex. I haven't built one. I built a quad personally, and we're using the latest DJI quad, the white one that you can spend. If you have a couple $1,000s to throw at the problem there, it's solid. And that one works nicely. As far as stability goes, we haven't had any problems with it. It's rock solid. And once I got bored flying quadcopters 10 feet away from the cliffs, I taught the geology students how to do it. Now they're running with it. I don't have to answer them. Going breaking other toys instead. The hexcopters can lift a lot more. And in fact, octocopters, try saying that fast, are what they generally use for video cameras.
Okay. We haven't gotten that far. We've only gone to hexes.
Okay. I think the primary advantage to the multiple, or adding more rotors, is just more lift rather than more stability. Once you got it stable, it's stable. You add more weight to it, it just gets more stable.
Interesting. And how did you get permission from your administration to fly the drones?
Next question, please.
There was a CSU order that we had to deal with a lot here to try to get permission to fly on campus. We finally managed to do it. But it was a lot.
We now have permission to do that for people who have FAA clearance
Right.
for drones.
Luckily, we skipped it.
At the time that I was doing this stuff with geology, I have an FAA, RC pilot license thing. A couple of years ago, they made everyone register because people realized you could put explosives on drone and fly them into Pentagon or something if you wanted to make a useless gesture. And so they made everyone register for that. I've got that registration, and as long as I wasn't being paid specifically for it, I didn't need that, and we forgot to tell the safety people on campus that we were flying because we were off campus anyway.
Sounds like a good solution.
Yeah, we basically avoided the problem. And now geology department's all legit. Anyways, we let them fly.
Yeah, the vegetation work you mentioned, and you showed a DSLR attached to one. Is that you're using the infrared sensitivity of the CMOS detectors in the DSLR with the IR filter?
That particular picture I just snagged off the web. Here's a picture of a nice heavy load that they're carrying around. They were actually using a little a lightweight Canon pocket camera, and they disassembled it and pulled the IR filter out. Yeah, there's an IR filter in front. And if you take that out and then reassemble it nicely, you got a pretty good chance of still having a working camera that is actually infrared sensitive. And in fact, the CMOS, I believe, is more sensitive to IR than to visible, so it really works pretty well. The focus point's a little bit different, but if you're just looking for which trees are lighter color in infrared than others, you really don't care. Yeah.
Would this happen, would you have drawn the same conclusions if it was under water pressure, for example, below sea level?
I don't think we would have even done the experiment if it was in water, because there's a lot of water drag. If you're trying to spin a propeller in water, there's a lot of drag. We would never even consider angular momentum. Air, we think, well, this is negligible.
Okay.
It's conservation of angular momentum that does it. Well, it wasn't. And it's not negligible at those Mach speeds. So, I think we probably just wouldn't have done the experiment because it would seem more obvious to us. It should have been as obvious as water anyway, because, it's not a torque-free situation. Oh.
Are there any design implications for developing high altitude drones or quadcopters from this result?
Depends on how high an altitude you want. Eventually, you get into satellites, which steer themselves or point themselves by conservation of angular momentum. Because you can do that with just electrical power, and you don't use up thrust. You just have a solar array. And so what we're talking about here is you can have a gyroscope in a satellite, and by changing the speed or orientation of that gyroscope, you can actually point your satellite to align your antenna. So that's the extreme case. Now, upper atmosphere case, well, back to this picture. With minimal air drag, you've got the initial kick from the change in speed of the props. And if there were no spring that this was pushing on, then that would be enough to give it this slope, and it would just keep going. Okay, so that'd be great for satellite. You give it a kick one way, and then when you get it to where you want, you kick it the other way to stop it. So it's an impulse to start it, another impulse to stop it. At high altitude, you do have drag. It may be a little bit easier. I don't know, I'm kind of fumbling around not knowing what I'm saying here, so I'll stop. Yeah.
The infrared for the crop health, is that like around 900 nanometers, or are you talking thousands?
I actually don't know what wavelength they were using for that. Any biologists here? They would. It's the near infrared.
Apparently there's a notch right around 910, 915 or something.
About the water absorption?
Water content.
Yeah. And they may be looking at that or near there. I don't know exactly what they're. Yeah.
While we have you, I'd like to ask a little bit about the CSU Fresno program.
Chico.
You know, the kind of, is that, what's that? Chico, I'm sorry.
Yeah, I can tell you all about Fresno. It sucks, so you should go to Chico.
We'll edit that part out of the recording.
Sorry. Chico, no, the Chico program. I mean, you want to talk about the variety of the faculty members and the research you're doing?
Yeah, we have 8 tenure track faculty. A bunch of new ones who just started recently. And a handful of old ones that are about to retire, and then me in the middle. We have about 40 physics majors. Actually, no, I think officially on the books it's closer to 80 or 90 physics majors, but we're never quite sure until we get to the upper division classes how many of them are really physics majors and how many of them are business major frat boys who thought it'd be cute to say they're physics majors. So we don't know. We graduate about 10 to 12 a year. And as I said, 10 tenure track faculty, 5 full-time adjunct faculty, and they're scraping the bottom of the barrel for who's going to be chair now because they just got me. I have till August to get any useful research or career work done, and after that I disappear into an office and go to meetings and do paperwork as chair. Ask me how I feel about that.
How many students go to CSU Chico, total students?
We have about 16,000 students at CSU Chico. And the biggest programs are business, engineering. We have a very large ag program. And we're one of the smaller departments, as we probably are on every campus. But we've got our classes big enough that the dean is off her back on canceling quantum theory, because it's too small. We're out of that particular danger zone, I think. We'll find out again next year when we try again.
Yes, they do on this trial.
Let's see, other things. We are no longer on Playboy's top 10 party school list. We have not been on that list for, I believe, 18 years now.
But the reputation persists.
And we try to stay off that list, but the reputation persists. We still have the business majors to go with. We have very active award-winning Society of Physics students. program, and I was the advisor of that for the last few years. One of our new guys, young and energetic guys, kind of take over now, and they're even more energetic and active than before. The biggest, most visible event we do every year is the pumpkin drop. We drop a fairly large number of pumpkins off of the 6th floor of Butte Hall. We have not missed the ground once. 27 years of doing this every Halloween. We have a whole skit we do with Galileo and Aristotle and Newton and Einstein all talking about various theories of gravity and testing things with big pumpkins and little pumpkins and pumpkins filled with water and flaming pumpkins, which gets some people on campus nervous, but we haven't burnt the building down yet either. The trick is using just the right amount of lighter fluid on the paper towel that's inside the pumpkin, and you have to have a hole in the bottom and at the top so you get this chimney effect. Beautiful flames all the way down, and then it goes out. Yes, because the lighter fluid's all burnt out. If you use 2 paper towels, then you have a clown at the bottom with a fire extinguisher ready to hit.
I have a feeling we wouldn't be allowed to drop pumpkins off of anything after what's been happening.
We didn't ask.
Right. We don't make jokes about fire too much anymore.
What did you guys burn down? What did you guys burn?
Town.
Oh, the town. Oh,
The county burned down, so we're a little sensitive about burning the fires. Although the campus, as you can see, was spared.
Yes.
But it was very tense for a while.
In general, we have found the SPS does very well if we get forgiveness rather than permission. So it works.
I have like a distance reaching question. So when we in this class we do a pre and a post thing where we look you up and we analyze you and guess what you're going to talk about basically.
Mm-hmm.
And I mean we know what you're going to talk about, but so it says you enjoy cycling. So is there ever a moment where you thought that like an Inspector Gadget where he has a bike that turns its wheels and goes up? Could you ever apply all this with vector speeds and that to bicycles and make them go up? Is that too far to reach?
Yes.
Well, I've never worried about doing that myself.
Okay.
Because although I race bicycles,
Yeah.
I'm not the person that people come to if they need a high-powered cyclist.
Okay.
And going straight vertical, there is a human-powered helicopter.
Okay.
I was within the last decade. I forget the exact year. You should look it up. I'm curious.
Okay.
But they had an Olympic quality cyclist flying a figure 8 inside a gymnasium. I think it was. It was pretty much the limit of human ability on that. I have done some work with the local cycling team, like how do we figure out whether someone's cheating on a bike race? Okay, one of the things that people are cheating with now, I can't do the doping stuff, that's biology and physiology and stuff like that. But one thing that people are cheating with now is motorized bicycles, okay, where it looks like a power sensing rear hub, but it's actually a motor, and then there's batteries in the seat tube or somewhere else hidden. And there have been cases where those have been caught. And so we got a race coming up in Chico on the 18th of March, and we have the physics department is loaning a infrared camera to the finish line. And you can see if someone's got batteries in their ground tube, well, the batteries are not 100% efficient. And so maybe you gain 100 watts from this motor, which is great, because an average cyclist on a good race, a good cyclist might be 600 or 700 watts. Adding another 100 gets you the race. But they're not 100% efficiency, so the batteries heat up. And the infrared camera, as the bikes go past, you see, hey, why is that tube of the bike real hot? Things like that. I've also done some GPS work. Some of it didn't work. I put a GPS sensor on a bike. We had a lot of problems with bike theft. I don't know if you have a problem here, but Chico is awful. So we have a GPS sensor that would tell where it is, and we left it on a poorly locked bike. And we watched it go away, and then it died. So somewhere out there is a bike thief who has a nice bike and a GPS sensor if he knows how to use it. And things like that. Not all of our experience work. In fact, I have to say the majority of them don't. Matt?
So one of the big things that I was impressed upon in high school is that a lot of people get into physics from some little thing they like as a kid, or some sort of like kinematics experiment they saw or they experienced. And I was kind of wondering if your flying the quadcopters and cycling and anything like that is kind of a derivative of what got you into physics, or?
No, I'd say physics was just the final manifestation of my ultimate nerdhood. That's a cyclist and running for me in high school was a survival technique. I didn't have to run all that well. I just had to run faster than the football players, because otherwise you could get a squirrely, whatever. So things like that. When I was 5, my mom gave me an old wind-up alarm clock, expecting me to take it apart. I actually put it back together afterwards, and it worked. And that's when she started getting worried. I might, show signs of strangeness. When I was 8, my dad and I made a solar-powered car for a science project. And I remember distinctly, the way we were running it was, we had a motor, just a little DC motor with little gear teeth on the end, and that was pressed up against the wheel, so that turned the wheel. And my dad was saying, well, we could make it go faster by getting a bigger wheel. And I remember arguing with him, no, that's not going to matter, because we're not turning the axle and we're not getting the advantage of the larger wheel, we're just turning the wheel. So the car is going as fast as the outside of this gear. And I tried explaining that thing, and I didn't have the right words, so I never could explain it, so I decided to go into physics so that I could explain it properly. I took the usual biology, chemistry, and physics. In high school, physics was the last science I took, so that's what I was thinking about when I went to college. I had a near miss with engineering. I got out of college and actually dropped out of grad school because it was horrible. It still is, but I worked for a while for Pasco Scientifics. I mean, that one. I worked for them, technical support, product development, for a couple of years, and decided I really wanted to teach physics most of all. That to me seemed like the second best job in the world. At the time, I thought it was the first best job in the world. I've learned otherwise since. And so if you're going to teach physics, well, I want to teach college physics and get a PhD, so I got a PhD. So to me, it wasn't, oh, let's go study something to get it, because I'm really interested in it. It was, let's go get a PhD because I want to do what I really want to do, which is be a physics teacher.
Well, that's a good point to wrap up. Let's thank our speaker again.